Alright, so today I'm gonna be explaining another important article with the title Towards the Dynamic Message Passing on Graphs. So this paper in NeurIPS 2024. So despite efforts to mitigate the reliance, existing study encounters message passing bottlenecks or high computational expense problems. So in this paper, we propose a novel dynamic message passing. It projects graph nodes and learnable pseudonodes into a common space with measurable spatial relationship between them. For example, this node has right, left, south, and north. But because there is a paper called GCN Geom or Geom GCN that uses the virtual nodes that allows us to connect nodes that are far away. They project it back to one of these four corners. And so they use the term virtual nodes. But here they use a different term. So they call it pseudonodes. And for example, virtual nodes, super nodes, different in different contexts they have, but the essence of all of them are the same. So you see the uniform pathway, but the dynamic pathway we can see it very easily. Also, it reminds me the dynamic routing of Geoffrey Hinton in his article on capsule networks, which of course was not scalable at that time. And even today, it's very hard to scale it. It's a very interesting idea, the capsule network, CapsNet. So they also talk about dynamic path routing between capsules and different layers. Very interesting. So this paper reminds me that, but let's go through that. The vanilla message passing applies node-centric aggregation constraint between adjacent nodes. During this segregation process, central nodes access their neighbors in an isotropic manner and aggregate multi-hop features iteratively. So the vanilla message passing relies heavily on the input graph structure, leading to over-smoothing, over-squashing issues. So, some methods directly model pairwise relation between nodes, but the dense relation causes high computational space complexity. Yeah, it's very easy to do that, but you forget this complexity. Other methods incorporate pseudo-nodes connected with all graph nodes to serve as message pathways. This is another extreme. Why do we need this pseudonode to connect to all nodes? It should be distributed. At least you should have multiple pseudonodes at different local areas of the graph. So because man always makes extreme things, because man is sinful, so man always creates extremeful, either only one pseudo or virtual node, or they just say very locally message passing. So the extreme here is GNN. Another extreme is a graph transformer, for example. So there are many intermediate things that nowadays the hot research area is in the middle, that have some locality and some global aspects. Of course, another research area is take care of the local structure, also positional encoding. All of these helps us to avoid over-smoothing, over-squashing, over-correlation, over-fitting, and low WL expressive power, but still GNN cannot do, for example, heterophilous graph. Look at the data set. The state of the art is just 50% for squirrels. There are two data sets that are very difficult. So there are room for improvement. Both graph nodes and pseudonodes are embedded in a common space with measurable spatial relation. Oh, this reminds me the paper GCN Geom or Geom GCN, that they project a node, any node that is far away, I mean, of course, it should be a local neighborhood, to either east, west, north, and south, the four corners of the node. Of course, each node has four neighbors in this way. Of course, your neighbors could be hyperbolic, not Euclidean like this. But the idea is that nodes that are far away can be projected to one of these areas. Look how beautiful it is. So that's why your brain is working. There is always some proxy nodes inside your brain. It has been discovered in your thalamus. As you do research in neuroscience, you will realize that there are some parts in the brain that are specifically related to the virtual nodes that we are doing it in artificial intelligence. But in real intelligence, it is in thalamus and different white area, different parts of the brain that are specifically designed by the Jesus Christ to be the exact function that these virtual nodes are playing the role. Because the two distant nodes, they should be connected to each other. If you do local message passing, it takes, for example, 100 layers of graph neural network to do this 100 hop. But through these proxies, through those virtual nodes that are in your brain is in the different regions, that enables us to connect different parts. So the related part of work is flexible message passing, reducing complexity for global message passing, recurrent labor for graph learning. This is also very related. So let's talk about the proximity measurement. To model complex relations, we assume that the embedded nodes have a nonlinear relationship in state space. However, modeling nonlinearity via operations such as path integral can be computationally complex. To address this problem, we approximate nonlinear relations with piecewise weighted inner products, taking proximity measurement between graph nodes as an example. Each node is divided into k pieces, and their proximity formulated as this. That there's a sum of these, and lambda I is the learning parameter. This is just a nonlinear function. Once you get this, then you can have the proximity. So you can always find the proximity. So any two nodes, there is a proximity measure that says how close they are. Pseudo edges based on measurable proximity between the embedded nodes. We now introduce how to obtain pseudo edges, and thus associate pseudo-nodes to input graphs. For each pseudo-node embedded at R sub u in the state space, it has pseudo-edges. So, pseudo-edges weights can be formulated like this network. So pseudo-node is U prime. And messages for embedded nodes. So we interpret the interaction between the embedded nodes as a message passing. To achieve this, both graph node and pseudo-node, those graph node and pseudo-node, learn their messages to be passed in the state space. As a result, graph node V and pseudo-node U can be described like this. So they have messages associated to pseudo-nodes to the graph nodes. Once you get that, then you know the global message passing. Because graph nodes perform global message passing based on their states, where pseudo-nodes serve as proxies. So given graph node states Q, pseudonode states R. So R is pseudonode, Q is graph node states. Now the global message passing process can be used, formulated as this diffusion, diffuse it, then we refine it, then we collect it. Because we need to find a kind of message passing between these pseudonodes, let's call it pseudonodes, and the graph nodes, the original normal nodes. So how do you want to do message passing? Through these equations. And for topology coupled message passing is employed to encode the local structure. The resulted local message passing process for graph node V can be formulated like this. Topology coupled message passing to encode the local structure. And then here we are concatenating them, giving to nonlinearity. Again, you update the M of locally the nodes. So implementing dynamic message passing. So we further develop a GNN model name N2 to move the embedded nodes to their optimal positions by feeding the states recursively into a single recurrent layer. And N2 learns the displacement of all embedded nodes in the state space and updates their positions. The changes in position reshape the spatial relations between the embedded nodes and thus reshape the dynamic message pathways. These dynamically evolving pathways empower N2 to adapt to the specific positions of the embedded nodes at each recursive step. So pseudonodes are randomly initialized in the state space. To adapt to a specific input graph, the model first diffuses graph nodes messages to pseudonodes, adjusting pseudonode states and corresponding accordingly. So given node messages M, graph node states Q, and pseudonodes, so pseudonodes are here. So we combine them to get your global message. It's a pseudonode messages that are collected by graph nodes, serving as query signals. Of course, I've seen a different paper, much more interesting than this. I also admire the paper Geom GCN, which is more natural. I mean, it's more, for me, it's more bio-inspired because it has better computational complexity, simpler is always better, and many other points. This one is very artificial, very artificial. And you need many different things that are not natural. So N2 performs both local and global message passing. At the local level, graph nodes exchange their own messages, collected messages, and graph node states Q. Through local message passing, graph node messages are generated in response to query messages. So N2 sends the updated messages to global message passing. And it updates the state of embedded nodes recursively with a single recurrent layer. So let's look at their experiments for node classification. The N2 is their model. They have for they have this accuracy. This is ROCAUC, except accuracy for Amazon rate. Here is the node classification. OGB proteins, OGB archive, and the metrics are either accuracy, ROC, AUC. For their model, they could improve some of the baselines. I mean, all of them, because these are the traditional. This is a propagation method, even Graphomer, and they also compared with Graphomer and Xformer. So you see, it's even better than them. Oh, this is very good that they can tackle over squashing. Because we have node classification, it's better to always report this TSNE visualization so that people can see the distribution of node classes. This will be even more interesting for heterophilous graph, because this is these graphs are more homophily, as you see. Most of them have the same color in each cluster, so it's more homophily, high homophily, maybe 89% homophily, so they use it for graph classification. Here, for protein is 77% mean, and their variance is 1.78. I mean, the standard deviation. And then node classification on small scale homophilic graphs. Oh, they mentioned it explicitly that it is a homophilic graph. These are homophilic graphs. So the heterophilia is very low, should be around, for example, 20%, 10%.